戴眼镜呢，狗狗有戴眼镜。
Yeah. So everyone mute your microphone, Yeah. Okay. So you all are seeing this question 3 here, right? Yeah. So you can see the question on your left, and you can see the it's like the solution on the right. Oh, so this question here, question 3 here, actually we analyzed last week already. Yeah. So you remember we analyzed the question last week. So let's have a recap. Okay. Let me go and look for my, here I am. Now, this one is quite a long question, right? So you recall that what we did last week. So we say that we go and read the question a few times, and then we pick up those phrases that the question repeat, right? And then by doing so, we actually able to highlight these repeated phrases. So things like machine set up correctly, right? You see, machine set up correctly. And then also these are good parts. Machine produces a good parts. And then we also say that machine set up correctly. This one set up incorrectly. That is also related, right? So we also go and put in. And here is another one. Good parts here. Okay. Right. So we have this set up incorrectly. Then we have this good parts here. And of course here, there's another good part, right? And also you can see here, there's a set up correctly. So remember, we did all this last week, right? So we go and pick up all those repeated phrases. And then we say that all these repeated phrases are important. So we actually go and define them as events, right? So you got this set up correctly. And we have over here, what do we have over here? Then we have this. Machine is set up correctly. And then we call it MC, right? And then the one set up incorrectly, well, that's also here. And then we call it MIC. And then how about the good part? So we have over here, a good part is produced, and we call it GP, right? So this is what we did last week. And then not only that, we also go and look up the numbers. Yeah, remember all these numbers, like 70% of the time, here 90% of the time, and then here 40% of the time, right? So these are the numbers given to us. Then we also go and write them in terms of all these events. Yeah, so this is what we did last week. So in fact, this is what we did last week. All right, so we have found that given probability of machine set up correctly is 0.7. That's the 70% of the time. And then from here, we also infer that machine set up incorrectly. That means the complement of machine set up correctly, right? So it's 1 minus this, then we get 0.3. Then we also have these two conditional probabilities. Probability that you get a good part, given that machine set up correctly, is like that. Okay, probability that you get a good part, given machine set up incorrectly, is like this. And then the last sentence here actually is to ask us to find this. What is the probability that machine is set up correctly, given that a good part is produced? All right, so this is the one. So this is where we stopped last week. All right, so tonight we'll continue from here. All right, so you want to find this probability, right? So you see here, well, of course, looks like very complicated, but there's one interesting thing that you see. Can you see this one is a machine set up correctly given GP? Can you all see this? Right? And then you notice that this one given, this given data is the other way around. It's a GP given MC. This one is MC given GP, right? This one is GP given MC. Well, I don't know whether you all realize this or not. So there's something here, right? There's something here. So, any significance? Well, actually, there's significance to me. Yeah, because from here, then I actually can figure out what is the method to do to solve this problem. Okay, don't know whether you all know how to solve this problem or not. So before we go and do some summary, let me ask all of you here. Anyone solve this problem already? Yeah, class, anyone or not? Anyone? There are 59 of you here. So anyone has solved this problem already? Well, class, if you have forgotten, last week I mentioned that in our class here, when I ask question, I hope that you will unmute and just reply verbally. So, any of you have solved this problem already? Anyone? Oh, no, not yet. Okay. Okay, then we go and do some summary. Okay, then we go and solve this problem. Okay, so here is the summary related to this problem. Okay, so the summary is like that. We are going to talk about partition. Okay, so we have a B1, B2 up to BK. We say that it is a partition of S. The S here is a sample space. So when do you say that this set is a partition of S there? Well, under two conditions. Okay, so we see there are two conditions here. But these two conditions, they are best described by a diagram. Okay, so I'm going to draw a diagram here. Hey, let me draw this diagram. Okay, so this one, everybody can see a rectangle, right? So this rectangle is like our sample space. Okay, sample space. And then I'm going to draw a partition of this sample space. Now, how to draw partition? Partition actually is just an English word. So it is well, just like what the word means. So you just draw some partition. Like that. If I draw like this, that means I partition the S into 3 pieces, right? Yeah, into 3 pieces already. So I can call this B1. Yeah, a bit difficult to write with my mouse. So this is my B2. And of course, this is my B3. All right. So this one, my B1, B2, B3, like what I draw here, actually is a partition of S. Now here we put B1 up to BK, of course that's in general, okay? So for this specific one is a B1, B2, B3. So we say this B1, B2, B3 is a partition of S if what? Now look here, look at part A. B1, B2 up to B3 are disjoint subsets of S. Now you look at your B1, B2, B3 here. Are they disjoint subsets of S? Well, I guess the key thing here is disjoint, right? You all know the meaning of disjoint? Disjoint meaning what? Got intersection or not? Disjoint? No intersection. Okay, so you can see that your B1, B2, B3, they have no intersection among them, right? So they are disjoint subsets of S. So everyone agree, y'all? So that means you have A here. Okay. Then only that, if you look at B1 union B2 union B3. Now, if you union all these 3, what do you get? Now, of course, if you union all these 3, you get back your S, right? So that is your part B. All right. So that's why I say these two conditions. In fact, these two conditions that make it a partition is they are best described by this diagram. Okay, so you remember this diagram, then you remember what is the meaning of partition. Is it okay? All right, and then also for this part B here, B1 union B2 union B3 is equal to S, right? And this gives us that probability of BI, when you sum it, probability of B1 plus probability of B2 plus probability of B3 will be equal to 1. All right, 1 is actually the probability of the sample space. Okay, so this is immediate consequence. All right, yeah. So in fact, this one here, you know, this equation here, summation of probability of BI equal to 1, this also help us to check whether your B1, B2, and so on, whether they form a partition or not. All right, so if the sum is not equal to 1, that means your B1, B2, and so on, it is not a partition of S. All right, because if it is a partition of S, the sum of probability of BI must be 1. All right, everybody got it? Okay. All right, so I think everyone clear of a partition already. Now the next thing that we come to is I'm going to introduce this term that's called total probability of A. Right? So suppose your A is an event of S. Then we got this term called total probability of A. Well, of course, it sounds like something very complicated, right? But actually, it is just probability of A. Right? Then you see, it's just probability of A. And then why you call it total probability of A? Why you got this word total? Well, that's because this probability is expressed in terms of the partition. And you see here, it's a summation of probability of A given Bj times probability of Bj. And then your J sum from 1 to K. All right, so you can see that it's in terms of the partition Bj. So when it is in terms of partition Bj, then we call this total probability of A. But it is just the probability of A. Okay, so this one is also done. All right, let's go to the next page. Now, the next page is called Bayes' theorem. Let's look at this Bayes' theorem here. Now, over here, we need to have a partition. Yeah, so you can see you have a partition here. Your B1, B2 up to BK is a partition of S. And then your A is an event of S. Right? And then you have this formula here. Now, this formula is like that. You see here, for R equal to 1, 2, 3 until K. Can you see this R here? You can see I highlighted, right? It is also in red color. And you see this is the R here, the subscript here, the R. Yeah, this is the R here, this is the R here. All right, so your R can take 1 or 2 and so on until K. And this is the formula to calculate probability of BR given A. All right, so you see how to calculate probability of BR given A, where this BR actually is an element of the partition, right? Your A is an event, right? How to calculate this probability? So this is the formula. Now, there's a numerator, there's a denominator, right? So numerator is like that. Denominator, now you look at the denominator, This denominator here, now it's a sum. Summation of probability of A given Bj times probability of Bj, right? This one is actually the probability of A. Yeah, this is just the probability of A. All right. Yeah, this one is just the probability of A. Okay, now, how do you know this is probability of A? Because this is just the total probability of A. This is the one. So it is just the total probability of A in the denominator. All right. Okay, now, yeah. So this whole thing, this formula here is called Bayes' theorem. Okay, now, all right. So now we know Bayes' theorem already, right? Let's go back to our this question here. So remember, just now we say we want to find probability of MC given GP, right? And then I pointed out that we have something here that's called GP given MC, right? So I say, well, this one is like opposite. So this one is like opposite. Can you also see this thing inside the Bayes' theorem? You know, this thing that's opposite, right? GP given MC, right? And then here, this is an MC given GP, right? Do you also observe something like that in the Bayes' theorem? Then is your Bayes' theorem. Do you also have a situation like this where you switch these two?
Yeah, pretty much it.
You can see, right? Where do you see it there? Here, the left-hand side. You got probability of BR given A. And then on your right-hand side, you have A given BR. Can you see? This one is BR given A. And then over here, you got A given BR. Right? So it is because of this that I think we can use Bayes' theorem to do this. All right, so this is from the observation because I'm also familiar with Bayes' theorem. So I know that Bayes' theorem also got this kind of thing, right? Then here also got this kind of thing. So therefore, I think that possible to try Bayes' theorem. Is okay? All right, so now you know why we want to use Bayes' theorem. Okay, now let's go and use Bayes' theorem. Now, to use Bayes' theorem, you look at the condition. What do you need? You need a partition. All right, so you see, you need this partition B1, B2 until Bk. Right? So we must go and find a partition here. Right? You need to go and find a partition here. And you remember what is your partition or not? There, your partition is like this. And you know, like that, your B1, B2, and so on must be disjoint. And then when you union, you must get back the S. And the summation of probability of BI must be equal to 1. Right? That's partition. So over here, what do you think can form partition? You look at the things that you have. What do you think can form partition?
MC and MIC.
Yes, it's a MC and MIC. All right, so we go through you suggested MC, MIC, right? So we really must go and check these two really form partition or not. All right, so first of all, let's check condition A. B1, B2, well, now because you only have 2 items, right? So you only got B1, B2. Okay, so A, okay, let me type here. So maybe I type here. Maybe I type this B1 equal to MC. And then I type here B2 equal to MIC. Is it okay? All right. So we want to call this B1, call this B2. Then you must really check your B1, B2, are they disjoint subsets of S there? Disjoint or not? And got anything intersection? Machine set up correctly, machine set up incorrectly, any intersection or not?
No.
Any intersection? No, right? Yeah, they are totally different, right? Totally opposite to each other, right? So no intersection. Okay, so B1, B2 satisfy A. Then the next one is B1 union B2. Does it give you the S? Well, actually, in this question, we also don't know what the S is, right? But let's check the probability. Probability of B1 plus probability of B2. What do you have? Probability of MC plus probability of MIC. What is it there?
1.
Get 1.
Yeah, you can see it's 1, right? Yeah, because they are complementary to each other. So of course, the sum is 1. So it satisfies this. Yeah, certainly satisfies this. So maybe we come back to this question. B1 union B2 equal to S. So you imagine your machine set up correctly. Then you go and union machine set up incorrectly. And it's supposed to give you S. Can you describe S? Well, sometimes can describe that. Sometimes very hard to describe that. How about you try? Can you tell me what you think this S is, this sample space? Machine setup. What?
Machine setup.
Yeah, correct. It's the setup of machine. All right, so your S here, your sample space here, you can consider it as the setup of machine. Is it okay? Okay, all right, so we got our partition already. Very good. Now we go back to our Bayes' theorem. Bayes' theorem. Okay. All right, you got a partition. Then the next thing is, do you have event? Then you see here, A is an event. A is an event of S. Well, you look at your question here, we only got a GP here. Right? So we only got a GP here. So if we don't call this A, then call who A there? Right? So we let A be GP. A good part is produced. Then everything will fall in nicely. All right. So you see, everything really falls nicely. Your probability of MC is your probability of B1. Probability of MIC is probability of B2. Then your this one, if we do the translation, GP is A, right? And then what now? Your MC is B1. Yeah, so this is your 0.9. And then of course, the next one is your A given MIC, which is B2. All right, so your A given B2 is 0.4. And what about this thing? This is the thing that you want to find, right? So this actually translate to a probability of B1 given A. Yeah, everyone can see that or not? Yeah, so you see, you actually want to find probability of B1 given A. Well, isn't it just your Bayes theorem? Right, then you want to find probability of B1 given A. Then you just follow this formula here. All right, and everything is here. Okay, not? Yep. So you just go and do that. And then you just use Bayes theorem to write all this. Now here, of course, I still keep to the original names. I didn't go and translate to A and B1 and B2, all that. But it's just Bayes theorem. It's okay? Then you just put in the numbers. So is this okay, class? I know that this one you need some time to figure out. Okay, so you just go and do all this translation, and you'll see that this is just our Bayes theorem. Okay, not? Okay, y'all. Yeah. Yeah. Oh, just now someone put in the chat box about this A, is it? Sorry, because my screen full already, so I don't really look at the chat. So you got anything, you just unmute and talk to me, okay? Yeah, I like people to talk to me. Okay, so now this question considered okay already, Now let's go and do the next question. To do the next question, let me do some more summary. Okay, here. Now the next one is I'm going to talk about this distribution function. Okay, distribution function. Now this is the one. Distribution function of a random variable x. Now your x here, this random variable, it can be discrete, can be continuous. All right, so we also have this distribution function. Now distribution function is denoted by capital F. Well, you can see it here. I see capital F here, right? So fx is a probability of big X that's equal to small x. Now you can see that the two small x, I see it in the same color and also highlighted, right? Meaning it's the same small x. Now the big X there, what is the big X? Well, it is the random variable that big X. All right, so you can see that our distribution function actually is a probability. It is a probability that big X less than or equal to small x. Okay, and this is we also call it capital F and the small x. All right, so this is the distribution function. So in fact, this line is the definition of distribution function. Okay, then of course you see another two lines, right? Well, that one is we consider when x is a continuous or discrete random variable. So when x is a continuous random variable, then this probability here, probability that big X less than equal to small x, becomes an integral. So here we just go and integrate the probability density function, that's the small f, from lower limit to upper limit. Lower limit here is minus infinity, upper limit here is the small x. All right, so it's like this. And when x is a discrete random variable, then this probability of big X less than equal to small x, right? Here you need to sum the probabilities. All right, so this is probability of x equal to k, and you sum up the k until x. All right, so this is what it is. Is it okay? All right, so we got basically like two formula. So when x is continuous, we use this. When x is discrete, we use this. Okay. All right, so now this is distribution function, right? So let me go to a distribution function question. Okay, so let's look at number 6 here. Let's go and read the question. So let X be, let me bring out a highlighter. So let X be, now X is what? X is of course the variable, random variable. Let X be the number of years a particular type of machine is in good working condition and need no replacement. All right, so it's quite a long one. Yeah, so it's the number of years that the machine is okay, is in good condition. Now assume that X has the priority mass function. All right, so X has this priority mass function, right? And you see here P1, P2, P3, P4, P5. All right, well, the fact that they mention this word, this phrase, priority mass function, that means your X is a discrete random variable. Right, and all these P1, P2, P3, P4, P5, well, it means priority of X equal to 1, priority of X equal to 2, priority of X equal to 3, and so on. All right, okay, now. Okay, so now what do we want to do? We want to find the distribution function capital F. And then later on, we want to sketch it. Okay, and then of course, we got a small question here also. Well, that one we'll do later. Okay, so this is a question of a discrete random variable, and we want to find the distribution function. Okay, right. So if we look back at our, just now our summary, right? Okay, now our X is discrete, so we have to sum up the probabilities. It's like the priority mass function, right? So we need to sum up until the small x, right? So this is what we are going to do. Okay, so let's see how we do it. Okay, so here we are. Okay, so first of all, let's copy the question. So this is our X. So I just copy down the X. I also put in the priority mass function, the P1, P2, P3, P4, P5. So these are given, right? And then, well, you realize that I go and draw a line. Yeah, you see this blue line here, right? And then I go and put down the 1, 2, 3, 4, 5 here. You know why I put down this 1, 2, 3, 4, 5 or not? Why I didn't go and put down 6, 7, 8, 9, all that? Anyone? Anyone, class?
You probably can't stop at 5.
Oh yeah, because our priority mass function only until 5. So that's why I put only until 5, right? Yeah. So actually these values that I put on this line, these are the values that X can take. Our big X cannot take any value. It can only take values 1, 2, 3, 4, 5. Okay, all right now. Okay, yeah. Okay, then I'm going to find the distribution function. And you can see here that this is the definition that I write down. Distribution function actually is this definition. All right, so in fact, if you look at the definition, it's sometimes it's easier for you to figure it out. Okay, now. Okay, now this real line here, where I put the 5 numbers, 1, 2, 3, 4, 5, right? So these 5 numbers actually divide this real line, this is a real line, into how many segments? 6 segments. All right. What are the segments? They're here, below 1, between 1 and 2, 2 and 3, 3 and 4, 4 and 5, and more than 5. All right, so 1, 2, 3, 4, 5, 6. Divide the real line into 6 segments. Okay, and I'm going to find the distribution function for small x in each of these segments. All right, we'll find segment by segment. Okay, so first of all, we'll go and do, let me change to this one here. So we'll go and do the first segment. Now, first segment, that means somewhere here, right, below 1. So for small x below 1, so imagine your small x here is below 1. Below 1 means less than 1. Okay, not? So you notice that I always start from definition. Fx is probability of big X less than small x, right? Okay, now very easy. I want you to imagine your small x below 1. Can you give me a number less than 1 or not? Anyone can give me a number less than 1?
0.
0.9.
Say again.
0.9.
Sorry, can't catch what you say.
It's like 0.
Is 0 your first answer?
Yeah, kind of. Yeah, 0.
Oh, you want 0, is it? Okay, fine.
Or maybe 0.9, like either one.
Okay. Maybe we take 0.9. It's better. Okay, so let's take 0.9. So you imagine that your small x less than 1, right? So imagine your small x is 0.9. Okay, then you go and see, you put your small x as 0.9 here, and then you go and see probability that big X less than or equal to 0.9. Can your big X less than or equal to 0.9? What do you think? Your big X.
It's highly possible.
Yeah, it's not possible because your big X can only take values 1, 2, 3, 4, 5, right? Like what is stated in your probability mass function. So it's not possible for your big X to be less than or equal to 0.9, right? I hope everybody catch that. So therefore, what is this probability there if not possible? What is this probability?
0.
Yeah, it's not possible. So the probability is 0. All right. So just like that. Nothing complicated. Okay, let's try another one. So we're done here already, right? So the next segment will be here between 1 and 2. So this is for x greater or equal to 1 less than 2. Okay, so you see, we still use the same definition. Okay, now another person, can you give me a number greater or equal to 1 less than 2?
1.7.
Okay, 1.7. Okay, everybody imagine your small x is 1.7. Now you tell me, what is this probability? Probability that big X less or equal to 1.7. Wow, then you think. Big X less or equal to 1.7. So that means your big X can be what values? Your big X can only be 1, 2, 3, 4, 5, right? So if it's less or equal to 1.7, then what can your big X be?
1.
Yeah, can only be 1, no? Okay, so it's just probability of X equal to 1. So there you get this. Yeah, everybody clear or not? I hope it's clear. Well, maybe we do one more. So this time our X is between 2 and 3. So you see, same definition, right? Yeah, so now between 2 and 3. So what do you think? What number you like between 2 and 3?
2.
Yes? Yeah, anyone?
2.5. 2.5.
Okay, 2.9. Right. So big X less or equal to 2.9. What can big X be? Wow.
1 or 2. 1 or 2.
Yeah, 1 also can, right? Yeah, so can be 1 or 2. So both are less than or equal to this 1.9, right? Yeah. So that's why you have like this. Is it okay? Then you can get this. All right. So I think you get the hang of it. So you just go to other segments. You see, you go to other segments, then you get all these things. And your last segment there, you will find that you actually include everything. All right. So when you sum up everything, you actually get 1. Is it okay? So now you got all your segments done already, right? So you go and collect all your answer. Then you put it down nicely like this, and this is your answer. So this one is your answer already. Just like your answer behind the tutorial sheet. Okay. Okay, now. Okay, now we go and draw this diagram because the question says sketch F. Hey, let's go and draw. Hey, so this is actually the diagram. This is actually the figure. All right, so you see the vertical axis is fx, horizontal axis is the small x. Okay. Now in this diagram, do you all see all this open circle? Yeah, you all see all this open circle or not? The one I highlight, you see all this open circle, right? You can see. You all know what's the meaning of the open circle?
You're not taking the value.
The point is not included. All right. So open circle meaning that that particular point is not included. All right, so why is it that we have open circle there? It's because of this. Then, like for example, here x less than 1, the value is 0, right?
Oh.
But for x equal to 1, you see here x greater or equal to 1, right? So when x equal to 1, the value is actually 0.4. Okay, so that's why you see here, this one, when x is 1, here at the when the y value is 0, right? It's an open circle. Because when x is 1, actually the value is 0.4, right? So that's how you get the open circle. Okay, all right. Okay, so we've done this sketch already. Now let's go and look at the last question. Okay, now the last question is here. What is the probability that the machine needs no replacement during the first 3 years? Yeah. Well, it's also put here. What is the probability that machine needs no replacement during the first 3 years? Right? During the first 3 years, probability that machine needs no replacement. All right? Now, to do this question, you have to link this question, the meaning of this question, you got to link it to your random variable x. Okay? Link it to your random variable x. So let's recall what is your x. Now, actually, the x is here. Then you just look at your question. Then here, your x is what? The number of years a particular type of machine is in good working condition and need no replacement. In short, what is x? X is the number of years that the machine is okay. No need any replacement. All right or not? No? Okay, so now you know the meaning of x already, right? Number of years that the machine is okay, no need to replace. Yeah, so what about, you come back to your problem. What is the probability that machine needs no replacement during the first 3 years? Meaning that your x can take what values? You think about it. X is what? The number of years that the machine is okay, right? So now they're asking you, what is the probability that the machine needs no replacement? That means the machine is okay. What is the probability that machine is okay during the first 3 years? So what can x be?
0, 1, 2.
Ask what can x be?
3.
Oh, yeah. 3,
Wait, no replacement for the first 3. So
0, 1,
more than 3.
Can it be 3? Can x be 3?
Yes.
Everyone agrees or not? X can be 3, right?
Yeah, I
Cannot?
pretty much think so.
Everyone agree, right? That x can be 3, right? Because when x is 3, meaning that 3 years it is okay, right? So it fulfills this. That machine is okay during the first 3 years. Is it all right? So x can be 3. And can x be 4? 4 can or not?
Yes.
Also can.
We can.
Cannot? 4, when x is 4, meaning that this machine is okay for 4 years, right? 4 years it is okay. So if it is okay for 4 years, then you think first 3 years okay or not?
Yes.
Yes.
Yeah, also okay. Yeah. So by the same reasoning, it can also be 5. So x can be 3, 4, 5, right? Yeah. So at least 3, 4, 5, everyone agrees. Can x be 2?
No.
Because here there's a problem. X is 2, meaning that machine is okay for 2 years. Then what about the first 3 years? Only okay for 2 years. Then the third year, then cannot. Okay, so therefore it cannot be 2. And likewise, it cannot be 1. Okay, so therefore we find that the probability is probability of x greater or equal to 3. So that means 3, 4, 5. Okay, all right, so this is your answer. Any questions? Okay, then we do the next one. All right, let's look at the question 7 here. So question is on your left. Wow, this one quite a long story. Yeah? So we got this supplier of kerosene. I'm sure you all know how to read. Well, now I saw this X here. I got my X here. So X here, this is my random variable, right? So my X here is the weekly demand in hundreds of kiloliter. And the relative frequencies for the demand are adequately modeled by this. Okay, modeled by this. Okay, now here, I see this fx here, right? So I shall interpret this as the probability density function. Okay, I see this fx here, all right? And I shall interpret this as the probability density function of x. And since this one is the probability density function, it means that my big X here is discrete or continuous. Class?
Continuous.
Yes. So my X is continuous. Okay, not? Yeah, so X is continuous. Oh, okay. So what are we going to do here? I believe that we need to find F. Okay, so we want to find the distribution function F. Okay, so here we are having a continuous random variable. We are given the probability density function, and we are going to find the the distribution function. Okay, the capital F. Okay, so let's go and do that. Okay, so we are looking at the solution over here. So you see, I copied down this probability density function, right? Now, this probability density function, well, it plays a very major role in finding this distribution function. So we need to look at it in detail. All right, so you realize that it has 4 parts. Yeah, you can see it has 4 parts here. X less than 0 is 0. From 0 to 1 is x, and then from 1 to 2 is half, and then x more than 2 there is 0 again. All right, yeah. So I want to I kind of want to like express this information on a real line. All right. So therefore you can see my real line over here. Can you see? So I try to write all this down. Okay. So I noticed that the, how should I say? It's like the pivot points is like 0, 1, 2, right? Because at this point, the function will change expression, right? So I mark down this 0, 1, 2 here. And then x less than 0, your fx is 0, right? Yeah, but here, instead of putting fx equal to 0, I go and put fy equal to 0. Well, that's because later on, I know that actually we are doing integrate fy dy. So I go and put fy here. Well, easier for me later on. Okay, so instead of putting fx, I go and put fy. So fy is 0 for y below 0. Okay, yep. And then from 0 to 1, you see fx is x, right? Yeah, so that means fy is y. And then from 1 to 2, your fx is half. So that means my fy here is half. And then for x more than 2 is 0. Okay, so for y more than 2, I also get fy equal to 0. So this one, I hope everybody understand my diagram here. Is it okay? All right, all. Hey, now the next thing is, well, I really want to go and find the distribution function. Now, earlier on, we have this summary here, right, on your left side here. So we said that if x is continuous, well, then my fx is just like that. I'm going to integrate the probability density function fy dy from -infinity until x, right? Yeah, so that's like this. So that's why you see here, I just follow, right? And you see everything is the same. Yeah, fx is integrate fy dy from -infinity until x. Yeah, I'm following this. Okay. Right, come back here. Now come back here. Then you realize that I write something further. here, this is the lower limit is minus infinity, right? But you see, I write here is I start from 0. I don't start from minus infinity lah. You see, I just start from 0. Do you all know why? Let me highlight this point here. Do you all know why I start from 0 here instead of the formula, the minus infinity?
Because everything below 0 is 0.
Yeah, correct. Because of this, that you know, below 0, your probability density function actually is 0. So the part you integrate minus infinity to 0, that part actually is 0. Okay, so that's why you just need to integrate 0 to x. Right? All right, yeah. So this part is okay. Okay, now since this one okay, then let's carry on from here. Now this 0, 1, 2 here, it divides the whole real line into how many parts? 4 parts. Below 0, and 0 and 1, then 1 and 2, and then more than 2. All right, so that's why this distribution function will also be found in 4 parts. Okay, so first of all, for small x less than 0. So you just imagine that your small x is here, right? Less than 0. Okay, so formula, your fx is you integrate 0 to x, right? And then fy dy, right? Yeah. But you look here, your x is below 0. What is your probability density function over here? What's the value? It's 0, right? Yeah. So you're actually integrating 0. Okay. So if you integrate 0, what do you get?
0.
Yeah, you will get 0. Okay. I thought you are going to say something else after the 0. Okay, so this one is actually 0. Okay, yeah. And then now we go to the next part. So going to the next part, x is between 0 and 1. Okay, so now instead of this x, I see this eraser can work or not. It really works. Okay, so now my x is here. So now my x is greater or equal to 0, less than 1. All right. And then, well, formula is the same. You still integrate 0 to x. Yeah. Fy dy. So imagine you integrate from here to here, right? Your fy, what expression are you going to put for your fy?
X.
Your fy is what?
Y.
Fy is y. Okay, yeah, your fy actually is y. Yeah, so integrate y dy. Is okay? Then you just go and integrate. Yeah, everybody okay here? This second part also okay? Okay, so now I'm going to go to between 1 and 2 lah. So let me go and clean this away. And let me go and draw a small x here. So now I'm going to bring my small x here. And I'm going to integrate from 0 to small x. From here to here. Yeah, everyone can see, right? From here to here. Now, from 0 to x, can you tell me your fy, what is the expression? You integrate 0 to x, right? What will be the expression of the fy? Are you going to take this one or you are going to take this one?
Fx is plus the fy and fy.
Well, from 0 to 1, your fy is y. From 1 to x, your fy is half. Is it okay? So here you actually need to split the integral. Yeah, so that is this one, right? Yeah, so as I say, here you need to split the integral because your fy is having 2 different expressions. Right, so you see here, I split 0 to 1 and then 1 to x. Can you all see that? Yeah, so I split 0 to 1 and then plus 1 to x. Yeah, and then you just put in the correct fy here. So fy here is y, and then the fy here is half. It's okay? So that's why you get this. Everybody okay? All right, then we look at the last one. Now we are here, x greater or equal to 2. Hey, let me go and draw that. X greater or equal to 2. So it's not here. Now I am here. X greater than 2. So my small x is here. I'm going to integrate from 0 until here. Right? Then you are going to tell me. Are you going to tell me this? Oh, I know already. You integrate 0 to 1 plus 1 to 2 and then plus 2 to x. And then you just go and put in your fy, the respective fy. Is this what you are thinking?
Yes.
Oh, this is what you are thinking, huh? Hey, but this is not what I'm thinking.
One.
I put 1. You see, I just put 0 to 2 and then I put 1. Why I put 0 to 2 there is because from 2 to x, that part is 0. So I can just put 0 to 2, right? So I put 0 to 2 and then I just put 1. Did I really go and calculate? Do you all think I really go and integrate and get 1?
No.
No, I don't. Then how do I know it's 1?
Property of PDF.
Yeah, property of the PDF. Okay, what is the property of PDF? The total area under it is 1, right? Yeah, the total area under it is 1. Now, let me show you just a few slides back. Here. Can you all see this or not? Your probability density function, you integrate over the whole real line is 1. The graphical interpretation is that the total area under the probability density function is 1. All right, then the total area underneath is actually 1. All right, then how do I know that from 0 to 2 is the total area? How do I know from 0 to 2 is the total area?
Cause anything above 2 0.
You look at your probability density function. It only has something from 0 to 2, right? Yeah. Below 0 is 0. More than 2 is also 0. So that means the area that you have is only from 0 to 2. Only from 0 to 2 you got something. All right. So from 0 to 2 actually covers the whole area already. So that's why it's 1. Everybody okay? Any questions? Hey, yeah, no problem, right? Hey,
I got question. It's like infinity to negative infinity to positive infinity, right? It's like the same as 0 to 2. So
yeah, yes.
Infinity also.
It's the, when our summary here, when we put minus infinity to infinity, that is in general. But you look at the expression of the fx, you can see that until, it's only non-zero in a certain interval, right? So that means your area is only in that interval. Outside, no area. So in our case, the only area that you have is 0 to 2. Because our problem is like that. You see here? Below 0 is flat. More than 2 is also flat. Right? Flat 1, no area. So it's only from 0 to 1, it has some expression. And from 1 to 2, it has some expression. So only this one, you got some height, and that gives you some area. All right? Outside is totally flat.
Okay.
So in fact, you all can go and draw the graph of this. Right? The graph of this is something like this. It's an x here, and then it's a constant here. All right, and then outside is all flat one. So you only got from here only. You only got your area from 0 until 2. 0 until 2. Outside, all flat.
Okay.
Yeah.
Thank you.
Okay. Yeah. Okay, then we go and sketch this function. Oh yeah, we go and collect our answers first and then write it nicely like that. Then after that, you can go and draw a graph. Okay. So this is the graph. and it's a continuous graph. So there's no no open circle here. All right, now. Okay, well, it looks like got some people type in the chat. Is it? I see. So you all check among yourself. Okay, all right. Okay, so let's go to the next question. So we actually complete this tutorial already, and we shall go to the next tutorial, and I will do a summary. Okay.
Professor,
Yes.
I don't have a question.
Oh, okay, fine.
Can you rewind back to the section x less than 0?
You mean this one?
Yeah. Oh, that. So since x can't be less than 0, why is it possible that it becomes the upper bound of the integration?
X can be less than 0. I mean, our small x here, you know, our this distribution function, the x, actually, our x can be any real number. Our x can be any real number.
Oh yeah. No. I'm talking about the equation below that. So x is less than x is less than 0, right? But
yeah.
Why is it the upper bound of the equation since it's less than 0?
I mean, I put 0 to x, right?
Yeah. Why is it less?
Well, actually, this lower limit and the upper limit of the integration. There's no rule to say that the lower limit must be a smaller number, the upper limit must be a bigger number.
I got it.
Yeah, so there's no rule to say that your x must be more than 0 lah. Although we often when we do that time, we often want the upper limit to be more than the lower limit. But actually, there's no rule to say so.
Okay. Thank you.
And why this one is 0 there is because our fy here is 0. Okay.
Yeah.
It has nothing to do with this number is actually below 0. The main reason is our fy in this interval is 0. So since we are integrating 0, then we get 0. Okay. All right. Okay. So now let's go to another summary. So we are into tutorial 2. And I'm going to summarize this normal distribution. So this is a very famous probability distribution. And I think you maybe have studied it before. Okay. It has another name. In case you don't know, it has another name. Do you all know what is another name? Anyone? Instead of normal distribution, what can you call it?
Bell curve.
No lah, it's not called bell curve. Bell curve is not a formal name. It's called Gaussian. Okay, so Gaussian distribution. Yeah, so Gaussian distribution, normal distribution, they mean the same thing. Okay, now just now you all mentioned bell curve, right? Well, the probability density function is a bell curve. All right, so this normal distribution, the probability density function is a bell curve. Yeah, so you can see that this is a symmetrical bell-shaped curve, and it has 2 parameters, the mean and the standard deviation. Okay, so this x here is a normal random variable. So it is having this normal probability distribution, and this is the short form that we write it. Okay, it's a short form. So when you see a short form like that, what does that mean? So it means x, that's our random variable x. And then you see this thing, the curly thing, right? It's called tilde. Okay. Do you all know how to spell tilde? Right, it's tilde. Okay, so x tilde. Now this tilde means is. So x is Then n, n means what? Normal. X is normally distributed, and then you bracket, then you got these two numbers. So the first number is the mean of x, that's called mu. The second number is the variance of x. Variance is actually standard deviation square. So that's why you put here sigma square. It's okay. So it's a mean comma variance. Oh, okay, yeah. So this normal random variable is a continuous random variable. So the probability density function is a bell curve, right? I don't know whether I got a bell here or not. Okay, here no bell. Maybe I draw a bell here. Or I draw a bell later. Okay. So it's a continuous random variable. And then we have a standard normal table. Okay, we got a standard normal table, which I will show you in a while. So this standard normal table is a very special one. So that's why we call it standard normal. So it's actually N01. Now you remember what is the meaning of N01? N means normal, right? 0 here means the mean is 0. And then the 1 here means what? It means your sigma square is 1. Sigma square is 1. Then of course, if you square root, then sigma is also 1, right? So that means the standard deviation is 1. Yeah, so the mean is 0, the standard deviation is 1. Yeah, so for this special normal random variable, we give it a special symbol also. You don't call x, you call it z. So this is the z here, right? And it is called standard normal. Now, our table, as I mentioned, is the standard normal table. So it's only for z, all right? Yeah. So that means that when we want to calculate normal probabilities, all our normal x, all the x here, you got to change it to z. Okay, yeah, just change it to z. And how to do the change? Well, here is the change. Suppose your x is normal, the mean is mu, the variance is sigma square. Now to convert this to z, this is what you do. You take this x, you minus the mu, and you divide by the sigma. Is it okay? All right, all. Okay, so we have x minus mu over sigma. So this is a standard normal. Okay, now, all right, so this is the way we do the conversion. All right, so maybe at this point, I go and draw the bell curve. All right, so bell curve. Well, you just imagine that this is a bell. Okay. Okay, so let me draw this standard normal here. So you can see that it is symmetrical about this line, right? Yeah, this line is the mean. So it is symmetrical about the mu. And in this case, the mean is 0. Okay, so for standard normal, it's symmetrical about 0. Okay, now, yeah, so that's it. Everybody okay until here? All right, so now let me go to the table. My table is here. Yeah, this is my table. All right, so this table will be given for your quiz, for your exam. All right, so everyone use this table. You don't use a calculator because your calculator, the numbers maybe are slightly different from this table. So we'll use this table as our answer. It's okay. So you just use this table. Okay, so first of all, let's look at the diagram here. So everybody can see this, right? So this one is actually the bell curve of a standard normal because you can see that it's symmetrical about 0, right? Yeah. So this is a bell curve of a standard normal. So the mean is 0, the standard deviation is 1, right? And you can also see the shaded area here, right? And you can see this area is shaded, right? And this shaded area here, I'm sure everyone can see the small z here. The one I circle here, you can see the small z, right? So this area actually is what? It's a probability because this is the probability density function. So the area under the probability density function is a probability. So this area is actually the probability of standard normal, the big Z, less than or equal to this number. This is your small z. Okay, it's the same small z here. Is it okay? Same small z here. Big Z less than or equal to small z. Now this one, well, actually is the distribution function, right? Yeah, like the distribution function that we just taught a while ago. And this one is the distribution function of the standard normal. Now, because standard normal is very special, so the distribution function now, we also give it a special name. So we call it phi z. Okay, in case you don't know how to spell it, phi. Phi. Yep, this is the phi. Okay, so this symbol here, although it looks like empty set, but it's not empty set, we call it phi. Okay, phi z. Phi z. Okay, so this is the distribution function of the standard normal. Okay, now. So now this standard normal table, actually, if you look at the headings here, what does it say? Areas under the normal curve. That means this shaded area. Yeah, they tabulate the area here. This shaded area is tabulated here. Now, how to read? How to read is very easy. For example, now you see here you got your z small z here, right? Then you see your small z is here. You see or not? There, here small z. Now over this side is the first decimal point. Then over this side, that will give you the second decimal point. All right. So if I just give you an example, now suppose you want to find phi of what now? Minus 3.4 minus 3.46. Right? Yeah. Then how to find it? Suppose you want to find my phi of minus 3.46. So over here, you see, you already got minus 3.4, right? Then where's the other 6? Then here, 0.06. So it will be this number here. Can everybody see that? Minus 3.46. So minus 3.4 is here, right? Then the second decimal here. So you use your finger, then you converge here. So this is your value. Yeah, everyone knows how to find this value, right? So it's quite intuitive. Okay, yeah. So looks okay already. So I think we can go to the tutorial. All right. And before I go to the tutorial, let me show you this slide. Now, this slide is actually a slide in our lecture notes. You can see that it's page 193A, right? And I want to show you this slide because our question requires this. Okay, our question is a probability question. Okay, so for probability question, we always want to know what is the random variable x. So that's why this slide, if I give it a name, it will be called what is x, right? What is the random variable x? Now, this slide gives you some hint on how to find this x. This is the first hint. Right, first hint is here. When the question talk about mean of something, variance of something, or standard deviation of something, then your x probably is that thing. Okay, let me give you an example. Mean of heights of students. Okay, variance of heights of students. Standard deviation of heights of students. All right, so what is your likely x? Your likely x is height of a student. Okay, yeah, your x is singular, not plural. So you will say x is the height of a student. Okay, now, so that's one example. Now, another hint is sometimes the question may tell you this. They will tell you something has, some probability distribution. For example, the heights of students can be modeled by a normal probability distribution. The heights of students can be modeled by a normal probability distribution. So what can your x be? Then you think your likely x maybe is the height of a student. Is okay? All right, so these are the two hints. So look out for these two hints and identify the X. All right. So shall we go to the tutorial? Yeah, so this is a tutorial. So we are on to question 2. Okay. So we are going to analyze this question. All right. So what are we going to analyze? So first thing, when you read the question, look up what is your X? What is your random variable X? All right. Because if you don't identify X, you don't know what to find. Okay. Yeah. So this one is important. So let's go and do that. So let me bring my highlighter. Okay. So Timeless is my highlighter on. Okay, it's on. So Timeless is a company that manufactures quartz crystal watches. Okay, so they manufacture watches. So the people there, they have shown that the watches have an average life of 28 months. Do you all see this word? Average? Everyone can see this word or not? Average?
Yes, yes.
I'm sure you can see. Does it ring a bell?
Your mean.
Mean of something. Average is mean, right? Oh, average is mean, huh? Wow. So you know, wow, this word mean of something. Average what? Average what? What is this? Life. Average life. Wow, I don't know whose life is that, though. Whose life, do you think?
The watch.
The watch's life. Okay, so looks like, I mean, from this sentence, I mean, just from here, if you use your hint, looks like, mean, watch lifetime. All right, so looks like maybe watch lifetime is your X. All right, so you keep that in mind. Then later on, see whether can get a confirmation or not. All right, so this average life is how many months? It's 28 months. Okay, so before something will spoil, then the watch also spoil. Okay, then come to the next sentence. The standard deviation. Everybody can see this, the word standard deviation. So that's the hint again, right? Standard deviation of what? Well, standard deviation of watch lifetimes. All right. So what do you think is your X? Is this your X or not? Watch lifetime? Yeah, possible. And then you compare with just now that one. Just now that one also watch lifetime, right? Then now also watch lifetime, right? So is it a confirmation? Yes, it is like some kind of confirmation. That means you're on the right track. Okay, so this standard deviation is how much? So it's 5. Okay, and we read further. And the distribution of lifetimes is normal. So what attract you is this word normal. Wow, normal. So what did they tell you? Wow, something has normal probability distribution. Wow, and what is that thing? What is the thing that has normal probability distribution? What is that thing? It is the distribution of lifetimes. So if lifetimes, all right, so it's lifetimes again. All right, so then you compare. Here also watch lifetime, right? Here also watch lifetime, right? And now also watch lifetime. So can you say your X is watch lifetime or not? Is it quite obvious now? Yeah?
Standard.
Quite obvious, Okay, so then we go and write it down. Right, so then we say let X be lifetime of a watch in months. Okay, right. And then, well, actually, we read so many sentences, right? It gives us more than just this X. It tells us that distribution of lifetime is normal. So your X is normal. So you see, it's normal. Do we know the mean? What is the mean? Average life of 28 months. So this is the mean. Your 28 is the mu. And then what is the standard deviation? Standard deviation 5. Right? So this is the place where you put the sigma square. So you put the 5 square here. Is it okay? Everybody okay? All right,
Standard deviation. I hate myself.
Okay. So this one is 5 square. Everybody okay? All right, Okay, so now we go to the first question. Right, now here is the first question. Now, if Timeless, that means the company, guarantees a full refund. All right, guarantees a full refund on any defective watch for 2 years after purchase. All right, you all understand this sentence? Guarantees a full refund on any defective watch for 2 years after purchase. Right? What percentage of total production will they expect to give refund? Oh, looks like very deep, huh? Don't know what they're asking, right? Okay, first of all, let's look at the first part. Timeless guarantees a full refund on any defective watch for 2 years after purchase. What does it mean there? Look at our solution here. Timeless give a refund on any defective watch for 2 years after purchase. Means they give a full refund if what happens there? If what
Means
happens?
if it is defective within 2 years.
Yeah, if your watch is defective within 2 years, correct? Yeah, if your watch spoils within 2 years, they will give you refund. Everybody can understand that, right? Yeah. So if your watch spoils within 2 years, company will give you full refund. Okay, now not just like that. Now, watch spoils within 2 years. You got to relate it to the lifetime of the watch. Okay, because your random variable here is X, you got to relate it to X. So watch spoils within 2 years. What does it mean? What is the lifetime of that watch? If your watch spoils within 2 years, what is the lifetime of that watch?
Less than 24 months.
Yeah, that means your watch lifetime is less than or equal to 2 years. That means your X, the lifetime, is less than or equal to 24 months. Is it okay? Now everyone understand why it is like that? When the watch spoils, means no more life. Okay, yeah. Watch spoils means no more life. So watch spoils within 2 years means the lifetime is less than or equal to 24 months. Okay, now? All right, so now the question asked is, what percentage of total production will they expect to give refund? So that means they are actually asking you, what is the probability that they have to give refund? What is the probability that the watch will spoil within 2 years? All right, in other words, what is the probability that the watch will spoil within 2 years? So they are actually asking this. Probability that X less than or equal to 224. So this is the answer. All right, they're actually asking this. What is the probability that they need to give refund? What is the probability that the watch spoils within 24 months? All right. Okay, so now you look at this probability that X less than or equal to 24. Do we know how to do? Well, now it's much simpler because you know this X is a normal, right? You know the mean, you know the standard deviation, right? And what you need to do is to convert it to standard normal. Yeah. So we convert it to standard normal. Okay, how to convert to standard normal? Now look at your left side. This is your X, right? How to convert to Z? You take your X minus mu divided by sigma. Okay, so you go and do it here. Your X minus mu over sigma, that will give you your Z. Now your 24 here must also undergo the same thing. Minus mu is 28, right? Divided by sigma is your 5. Is that okay? All right, so you got this already. And then after that, you just simplify, you get probability of Z less than or equal to this, right? And this is actually your distribution function, phi of this. And then you just go and check the table. All right. So any questions regarding this? Okay. Yeah, so it's actually a very simple question, right? If we know how to interpret. Okay, so let's go and look at the second part. Okay, part B, okay, before we go to part B, so it's actually the percentage is quite high. So you see, if the watch spoils within 2 years, the probability is what? Wow, it's 21%. All right, it's rather high, right? Yeah. So now that's the basis for part B. So now part B says, if Timeless does not want to make refunds on more than 12% of the watches they make. So they don't want to have more than 12%. Okay, 21% is too high. So they don't want to have more than 12%. Okay, and how long should the guarantee period be? Okay, how long should the guarantee period be to the nearest month? So now we are talking about guarantee period. Now, class, actually in part A, what is the guarantee period?
2 years.
Yeah, actually in part A, although they never say guarantee period, but actually the guarantee period in part A is 2 years, right? If the watch spoils within 2 years, they give you full refund. All right, so now we need to find a new guarantee period so that the probability of giving full refund is what? Not more than 12%. Okay, so now let's have a guess. Let's have a guess. Let the guarantee period be X months. That's the new guarantee period. So if a watch lasts less than X months, then Timeless has to make refund, right? And they don't want to make refund on more than 12% of the production. So that's what the question say, right? Now, before we go further, let us guess, with this new guarantee period, do you think it will be longer or shorter than 2 years?
It should be shorter.
Shorter.
Yeah, should be shorter, right? Looks like common sense, So the shorter guarantee period, so that it will spoil after guarantee period. We hope that it will spoil after guarantee period. But also cannot be too short. I mean, there's something called customer satisfaction, right? Hey, y'all ever buy a watch and then the guarantee period is 1 hour? Anyone ever buy a watch, the guarantee period is just 1 hour?
No.
No, right? Yeah, you won't buy such a watch, right? Then you go out from the shop, then you walk 1 round, okay, finish already. So here, we also want the guarantee period to be long, but must satisfy the condition also. So this actually means this, right? Probability that big X less than or equal to small x. Small x is your guarantee period. So that means probability that the watch spoils within guarantee period. Now, this probability, the company say, cannot be more than 12%. So that means less than or equal to 0.12. Okay? Well, can you understand this or not? Right? Probability that watch spoils within guarantee period. Well, meaning that company must make refund. So this is at most 12%. Is it okay? All right, So this statement here actually will lead us to find the small x. All right. Okay, how to find? Now, just now we mentioned about customer satisfaction, right? So we try to get the largest x. We try to get the longest guarantee period that satisfies this, so that the company is also happy, the customer is also happy. Okay, all right. So how to make it longest? Well, less than or equal to, right? You just make it equal. That means really go up to the limit. Okay, then we'll solve the x from here. All right, now how to solve the x from here? Okay, this one is just a normal probability, right? Okay, let's change to the big Z. Change to standard normal. Okay, standard normal, x minus mu over sigma, right? Here, x minus mu over sigma. So that will give me my Z here. Then your small x here must also undergo the same thing. So x minus 28 over 5. Okay, then here this is your 0.12. All right. Now, after you change to here, then you realize that, now I got my standard normal. And this is just my distribution function, right? Which we call phi. That's our phi here. Okay. Phi of this thing is 0.12. All right. So this is going to give us the small x. Because now we are going to the table to look for this number. We are going to look for the 0.12. Okay. So let me go to the table. Now, table on your left side. Okay, then you see, wow, so many numbers here, how to look. Now you are looking for this number, okay? You are going to look for this number 0.12. Look from where? This is your area, okay? This is your area. So your area will be here inside the table. You go and look for the number 0.12. All right. Can you see the number 0.12 or not? You see the number 0.12? Maybe I bring further down. I think you should be able to find that. I think you should be able to find the 0.12. Can you see? Are you able to find the number 0.12 inside this table?
Negative 1.1. 1.17.
Yeah, I think you are looking at this, is it? You are looking at this, looking at this number, is it? There's a 0.121 here. Although it's not 0.12, but very close. And another very close one is this, 0.119. The rest are further apart. So it's this one, right? I mean, one of them. Okay, so you can find the 0.12 here, and you just read off these values. So you see what value will give you 0.121, what value will give you 0.119. Right, you just read minus 1.17, that is the 0.121, and then the other one is a minus 1.18. All right, that's the 0.119. All right, so in other words, you are getting these two numbers. Can you all see on the right side, I put down these two numbers. Okay, now, yeah, class. Okay, all. Okay, now there are two numbers here. Which one you want to use? Only one of them can be used.
0.119.
Why you want to use 119? Eh? Why you want to use this? Why you don't want 121?
Because must be less than 0.12.
Yes, because of this. Must be less than or equal to 0.12. All right, so we'll be using this. Yeah, so we'll be using this, right? So I think you must be thinking oh, then I just set x minus 28 over 5. I just set it equal to minus 1.18. Is it like that? Is that what you're thinking? You just set this equal to minus 1.18. Is that what you're thinking or not? Actually, not quite. Not quite. Okay, so we say we'll be using this and we won't be using this. All right, so let me draw a diagram here. Yeah. Let me draw a diagram here. I'm going to draw the bell curve. Okay, so this one is my 0. Okay, this one is a 5 minus 1.18. So 0 is here. So minus should be here. Yeah, minus should be here. So imagine that this is a minus 1.18. Yeah, this is the minus 1.18. And this area here actually is this one. Okay, so this is the area minus 1.119. Is it all right? This area is actually this area here. Okay, so this area, this shaded area here is is a 0.119. All right, so that's what it is. I mean, graphically, that's what it looks like. Okay, so now you must remember that this area is 0.119, right? And your number is what? Your number must be less than or equal to 0.12. So meaning that this x minus 28 over 5, you can actually go up, go up all the way here, go up until you reach your 1.18. At the most, go up until here. Do not go beyond, right? Don't go beyond. Why don't go beyond? Because if you go beyond, suppose like here, I go beyond, right? Then if I go beyond, then I see that, can you see that we are getting a bigger area now? Right? Can you see? If I go beyond 1.18, I will get a bigger area. And then that bigger area, you have no control. You don't know whether it will be bigger than 0.12 or not. All right. So therefore, don't go beyond the minus 1.18. And that is why that number, x minus 28 over 5, is less than or equal to minus 1.18. You can go from here up to minus 1.18. Don't go beyond. Is it all right? Okay, yeah. So after this, click the wrong thing. So after this, then what we do is you just solve this. Now this is an inequality, right? You want to solve for the small x. So you just shift the terms. All right. You why like that? So you just go and shift the terms. So you get x less than or equal to this. And then you calculate this number, you get 22.1. All right. So actually you look at the front, you look at the back, you get x less than or equal to 22.1. Okay, so this is how we interpret it. X less than or equal to 22.1. So therefore, what is the maximum small x? The maximum small x is 22.1. All right, and if you want it to the nearest month, then that is 22. Is that okay? All right, now.
Okay.
Okay, y'all. So let me type here. I may not catch what I'm saying. So I'm saying that this sentence here actually tells us that the maximum small x is 22.1. Okay, all right now. And if you want it to the nearest month, and that will be 22. All right, yeah. Okay, now you got no question, right? Let me ask you a question now. Now this number we calculate, and it turns out to be 22.1, right? Suppose maybe I change some numbers here. The number calculated turns out to be 22.9. All right, so that means if this is not 1, imagine this is 9, x less than or equal to 22.9. So in this case, to the nearest month, what is the guarantee period?
22.
22.
22.
Yeah, still 22. All right, because the maximum x is 22.9. So you cannot go and put 23. Is it okay? All right. Wow, so I say all I have to say already. Any questions?
Yes, sir.
Okay.
For the probability part, can we just write x? The big x is less than x, not less than equal to. And can we just write in that way? Or is it invalid?
I don't quite catch what you're saying.
Okay, so and can you go to the previous page?
Okay.
Okay, so under the yellow highlight over there, can we just write as x, the big X less than the small x? Can we write it in that way?
This one is big X, this one is small x. What I do here is just change the less than or equal to, change it to equal.
Oh, no. What I'm asking is, can we just write big X less than small x? Is it invalid if I were to write that way?
You mean less than, is it?
Yeah, less than.
Oh yes, you can, because our big X is a continuous random variable. So whether you put equal sign here or not, it's the same.
Okay, and over there, why do you change from less than equal to just equal?
Oh, then cannot. You cannot write this. This one cannot, You cannot write this. Because our big X is a continuous random variable. So if you read our notes,
No. I'm not talking about that. I'm talking about the the yellow highlighted part. So it's less than equal. It's less than equal to 0.12, right?
Yeah.
But why do you change the sign to equal?
You mean why must have this equal sign, is it?
No. Why did you change the less than equal sign to equal sign on the next line?
You mean here?
Yeah, why can't we keep less
You
than
can,
equal
you can
sign.
keep it, you can keep it. Why I want to put an equal sign here is because later on when we go to the table, you want to look specifically for this number 0.12, right? I mean, you want to put a less than or equal to here is also okay. I mean, you will
Alright.
still look for the number 0.12 and you will still take the 0.119.
Okay. Yeah.
Yeah,
Got it. Thank you very much.
okay. All right. Yeah. So I think it's all right all. Well, class. So that's all for tonight lah. Well, okay, fine. So then I see you next week.
Thank you.
Okay, thanks, Prof. Get well soon.
Okay, thank you. Bye-bye. Yeah,
Bye.
bye-bye.
Ayun na.
Okay, bye-bye.